Hello and welcome to the second round of flipped classroom presentations. This one will be on significant figures, probably the second topic of interest in this first unit besides how to show work. Most of the topics are reviews, so you really shouldn't need much in the way of instruction on those, but just the details of significant figures, showing work, etc., I think are of key interest here. So significant figures are often baffling, I think, for most AP students and for a lot of science students in general. The gist of significant figures is that other than counting numbers, anything that's measured is by its nature inherently inexact. You can imagine the kind of devices that we used years ago, when I was your age, to measure mass, let's say, were less exacting than the ones that we currently use now, but ones down the line will be even better than the ones we use now. So maybe when I was in high school, the best balances that a high school could afford measured to the 10th of a gram. That didn't make them exact, not even when it ends in 0.0, even though people seem to think that means it's exact. And now, we have ones that measure to the 100th of a gram. And maybe 10 years from now, 15 years from now, high schools will have ones that measure to the 1,000th of a gram and so on, meaning that we can never really exactly know how much some measured amount really is, because theoretically there's always the possibility of a more sensitive measuring device. And so then any measured amount has some uncertainty in it. We don't really know how exact that last digit is. We certainly don't know any digits beyond that, which means that last one that we report is a little bit uncertain. And because it's uncertain, when you start using measured values with other measured values in mathematical operations, addition, subtraction, multiplication, division primarily, then you start to run into issues with the number changing its size. So when you multiply and divide, suddenly you may get a much larger, a much smaller number with many more digits than you had before, simply because of the way the multiplication or division turns out. And you may end up with something that goes on endlessly, and therefore you really can't report that you suddenly know something's mass or area, volume, to the 100 billionth of a milliliter, when you really don't. So that's kind of the basis of significant figures. We're just trying to keep measured values in mind when we report answers that use those measured values. A couple of quick things. Anytime you count a number, it's exact. So if I say there are 12 students in the classroom, there are exactly 12 students in the classroom. Those are things that I can count. I have a baseball player hits 35 home runs. He hit exactly 35 home runs. They weren't measured, they were counted. A lot of conversions between units, especially in the metric system, are also exact. So if there are 1,000 milliliters in a liter, that is an exact conversion. There's no limiting value there for significant figures in the metric system. Some other conversions are also considered exact. You usually are responsible for knowing those. They'll be indicated on your paper. Pretty much from there on, anything else you're going to deal with will be inexact, and that's, of course, where issues arise. How would you determine significant figures in a number? Well, if it's a counting number, of course, it has unlimited significant figures. If it's a conversion that's exact, it'll have unlimited significant figures. So, of course, the problems occur then with measured amounts. Really, it all boils down to zeros. If something has a non-zero digit in it, it's significant. So if the number 1 through 9 is in there, it's going to matter to your measurement. If in your measurement there's a 0 in there, because of our base 10 number system, that's where things start to arise. So a couple rules, and I think the more you do these, the more you'll be in touch with these. If a 0 is in between non-zeros, it matters. It just so happens that the number turned out that way when it was being measured. So 303, the 0 in the middle of 303 certainly matters. Zeros are also significant if they're after a non-zero with a decimal. The decimal point in science is really important. It indicates that you've measured a certain number of places. So you put that decimal in there, and that really is quite important. So if I write 300 decimal point, which is not a notation that you'll see anywhere else, that actually means I measured out to that last 0 and then couldn't really determine anything beyond that. So that number actually has 3 significant figures. It just so happens that 2 of them are 0. If I write 300.0, that means I measured out even one more place beyond the previous one, and that also happened to be a 0, so there are now 4 significant figures in that number. If I write 0.80 or just 0.80, the fact that there's a decimal and then the 80 means that I measured the 8, and then again it happened to be 0, that would have 2 significant figures. Things that aren't significant are when zeros appear at the beginning of a number. That's what I refer to as the decimal warning system. 0.52, it's simply designed to help you pick up on the fact that a decimal, which is quite small and could be easily overlooked, is present. And also James Bond notation of 007, those zeros don't count either, even though they may mean a license to kill. They're not significant in terms of scientific measurement. The not significant values with zeros can also occur. This is largely because of our base 10 number system. When you have zeros at the end of a number that doesn't have a decimal. So if I just say 40, that's sort of my inclination in a base 10 number system to round things to end in 0. So I would say, oh, about 40 or about 800. And that means that I really don't know very well about the 40 or the 800 unless I were to put that decimal in at the end that would indicate 40 decimal point. That has 2. In this case, the 40 would have 1, the 800 would have 1, the 2,250 would have 3, with the 0 at the end being uncertain and probably rounded because of our base 10 predilections. So, if we were to look at some of these example problems, and feel free to pause this as you look at it in case you want to go through and write down your answers, and then I'll kind of go through and write my answers for how many significant figures. You can kind of see how you did. So pause at any time before the spoiler alert. So spoiler alert, how many sig figs? In 412 meters there are 3. All of those are non-zeros, so all will matter. In the 32.05, the 0 is in between non-zeros. There's even a decimal to enhance its importance, so all 4 of those matter. In the 0.310, the leading 0, the decimal warning system, does not matter. The decimal then makes us worried about all others that follow non-zeros. So there's a 3, that's important, a 1, that's important, and the 0 follows a non-zero, so it's important. So the only one that doesn't matter there is that first 0. 220 grams, there's no magical decimal at the end here, so we can really only rely on the first 2 digits, the 2 and the 2, because that 0 we're not really sure about, so that one only has 2 significant figures. The 0.0025 seconds, again, decimal warning system doesn't count. The zeros that begin a number don't count. Only the 2 and the 5 would matter, so just those 2. 9.73 times 10 to the 17th. Scientific notation is really useful because scientific notation only uses significant figures. So all 3 of those, the 9, the 7, and the 3, are important. We'll oftentimes use scientific notation for large and small numbers that we often run into in chemistry to highlight what is significant. The last 2 obviously are related, one with the magical decimal, one without. The one without has the ending in a 0 that lacks the magical decimal, so we can only know that the 8 and the 2 zeros in between the 8 and the 2 are important, and of course the 2 is. So that one has 4, but the decimal at the end there in this last one lets us know that there should be 5 in that particular number. Any questions or comments, feel free to email or track me down or ask me in class. Okay, if you start putting measurements together using mathematical operations, again, that'll most of the time for us be multiplication, division, addition, subtraction. We'll worry later in the year about what happens when you start dealing with logs. But for now, this is where we're going to be limited to. So for multiplication and division, because the size of the number changes rather significantly, it is the least total amount in your measured values. So if one of your measured values has 8, but another one only has 2, you will have to round your answer to 2. If your measured values, one of them has 3, one has 4, one has 5, one has 6, you have to go with 3. It's essentially a limiting factor because the person that only measured 3 decimals worth of information prevents the final answer from being reported as accurately. If you're doing addition and subtraction, the numbers don't tend to change size quite as much, and so you're only really worried about the digits after the decimal. And so if a number has no decimal places and another one has 5, again, the one with no decimal places really limits how accurately you can report your answer, so you'd report your answer with no decimals, not 5. If one has 1 place after the decimal and one has 2, you report your final answer with 1. Okay, let's look at a couple examples of those as well. Okay, here we have a couple of questions about how many sig figs should the answer have. You may need to work these out in your calculator just to get a sense of what they should be, but I'm really not going to worry about what the number and the answer is as much as just how many sig figs the answer should have. Again, if you want to work these out before I give you the spoiler alert, go ahead and pause this, jot down your answers, and then I will be continuing onward when you hit play to give you the answers. Spoiler alert. Okay, here we go. The first one has 2 significant figures in 18 and 3 in 29.2. The least number applies because we're talking about multiplication here, so the final answer should only have 2. The second one, 36.25, has 4. The 1.01 has 3, and so we have to limit our answer to 3 since we're talking about the total here because we're doing division. When we do subtraction, we're only worried about the numbers after the decimal. 1 has 1, 1 has 2, so we do 1 after the decimal. In the fourth one, we've got multiplication again, and we've got 4 in our first number here and 2 in our second number there, so our answer will only have 2 significant figures. In our fifth one, we've got addition going on. So with addition, we're only worried about decimal places. The 408 has no decimal places, so we'll have 0 after the decimal. So I'll call that A period after decimal. And then 51 divided by 28.01. Again, we're back to the total number. 51 has 2. 28.01 has 4. So we will have 2 total in our answer. Hope this helps. Again, if you have questions, comments, either email me or certainly bring it up in class. Thanks.